Hello and welcome to today's lecture. So today we will have the first part in a series of lectures regarding graphs, which is one key data structure with associated algorithms that is used to solve many different types of problems. So the outline of today's lecture is that I will be talking about graph representations, so how to represent these mathematical objects in a computer, how to traverse them, so basically navigating through these graphs. Then we will introduce a number of algorithms for finding the shortest path between pairs of nodes. We will also look at the problem of finding all the shortest path between every pair of nodes in a graph. And finally, we will talk about how to find the minimum spanning tree of a graph. So these will then cover the labs 2.1 until 2.5. So a major part of the second lab assignment. So let's start. So a graph is a mathematical structure consisting of a set of nodes connected by a set of edges. So in this picture here, we see a graph with 6 nodes and connected by, in this case, 6 edges. So each edge connects exactly 2 nodes. And now the question is, of course, how do we represent this mathematical object in a computer? And the three standard ways of representing graphs are called adjacency matrix, adjacency list, and edge list. So the adjacency matrix is a two-dimensional matrix with all the nodes on both dimensions, so both the rows and the columns, which means that the number in each cell represents, if it's a undirected or unweighted graph, then it's an unweighted graph, then it's just a 1 to denote that there is an edge. If it's a weighted weighted graph, then the weight will be the number in that cell. So 0 means that there is no edge connecting these two nodes. And if it's a symmetric, sorry, I cannot talk to you. If it's an undirected graph, which means that the arrows basically goes in both ways, then of course the same number has to be, so for example, if there's an undirected edge between node 2 and 3, there has to be a 1 in both 2, 3 and 3, 2. So this clearly shows that it's a undirected graph. Then we have adjacency list, that's the second type. So here we have a vector of nodes where the value in each element here is the list of all the nodes that are adjacent, that are neighbors. So for example, we can take node 1, which maybe is the most interesting because it's connected to every other node. So we can see that all the IDs of all the other nodes are included in this list. And finally, we could just have a plain list of all the edges in this graph. So basically pairs of node identifiers. So these are the three common ways of representing graphs. Of course, they have different properties. So when it comes to the adjacency matrix, it clearly has order v squared space because it will be v times v number of cells. V here is the number of nodes. And if we want to enumerate all the neighbors of a node, then we have to go through the row or the column, depending on of this node, and we can find everything that's not 0. Those are the neighbors. And if we, for example, want to represent this is in C++, it's a very simple thing. It's just a two-dimensional vector. And this is very good for small or dense graphs. So that because then we need to represent everything anyway, or there is no real penalty for doing it. But it cannot be used to represent multigraphs. So if there are multiple edges between a pair of nodes, for example. Adjacency list on the other hand, has the space complexity of B plus E. So we need to store all the nodes, and we have to store all the edges, but nothing else. And here it's order k to enumerate neighbors, where k is the actual number of neighbors. So of course, if the number of neighbors is significantly lower than the number of nodes, then this may be smaller. And the way to represent this in, for example, C++ is as a vector of pairs, where these pairs are then the nodes identifiers. And this is very good for large and sparse graphs because it basically only stores what needs to be stored. And it can be used to represent multigraphs, so we can insert multiple of these edges into this list. And third and finally, we have the edge list. So here we clearly have to store all the edges, so it's clearly order E space. But of course, now we have to go through this whole list to enumerate the neighbors. So of course, E here is order of V squared. So I mean, in the worst case, if there is a complete graph, then it's a V squared number of edges. So of course, this number can be quite high. So, but there are very specific cases, like we will see later, namely, if we want to use Kruskal's algorithm to find the minimum spanning tree, then the edge list is the optimal data structure for that. So here in C++, we would store this as a vector of pairs between ints, or triples of ints, we can say, it's easier to say. So it's the from node, the to node, and the weight. If it's an unweighted graph, then we don't need to have this weight information. But yeah, that's usually nice to have anyway. So, and normally we will store these edges sorted by the weight. And as we will see, the prime example is Kruskal's algorithm. Okay, so I mean, in your toolbox, you want to implement all of these. Normally, adjacency list is used if the graph is large, adjacency matrix if it's small, or if it's very dense. So now we come to the problem of having a graph, and now we want to visit all the nodes in a graph in some structured way. And the first way we could do this is called depth first search. So this is it's a method which goes through all the nodes, trying to go as deep as possible as soon as possible. So the way we do this is that we keep a stack of unvisited nodes, and we initialize this stack to the start node. Then we just pop the first element on the stack. If we haven't visited, then we visit it. And then we add all the children of this node to the stack. So it means that now we will visit the children before we visit the next node on the stack. So this will then perform what we call a depth first traversal. And of course, it's clearly B plus E. If we have an adjacency list, if we have a adjacency matrix, then we need to go through each row every time. So then it's to find the neighbors. So that's why it's a V squared. Breadth first is very similar, but here, instead of going as deep as possible, we rather try to visit every node on the same distance from the start node. So the distance to the start node is of course 0. Then we add all the children to the start node. They all have distance 1. And then we add all the children to all the children, and they become nodes on distance 2, and so on and so forth. And the way we do this is by using a queue instead of a stack. So the only difference between, the implementation of these two is that we use a queue instead of a stack. So we visit the nodes in the order that they were added to this queue. And this can be very useful, for example, to find the shortest path out of a Unicost maze, for example. Then we have best first search. So here again, it's exactly the same as the two previous. The difference is that we will use a priority queue of nodes. So we have some form of cost function that we use to order these. So we always try to find, for example, the cheapest path or the shortest path or something like that to some goal. So we're trying to have a sense of goal. So we always take the node which has the highest cost. Otherwise, it's exactly the same as before. And then we also have A star. So A star is like best first search, but we add a heuristic for estimating the remaining cost. So for example, if we want to find the shortest path in a graph, we can, of course, we know the cost of going from the start node to where we are, and then we can estimate the total cost it will take, or the minimum total cost it will take to reach the goal node by basically taking the straight line distance between where we are and where the goal is. And we know that it's not possible to find a shorter path than this. But of course, in reality, most likely the path will be longer, but that doesn't matter. So the whole point is there is, as long as you underestimate the maximum cost, then this is what's called an admissible heuristic. And if we add this admissible heuristic to the cost, then we find a faster algorithm or a faster search to take us to the goal. And it's also optimal and complete. So what can these be used for? If we have an undirected graph, then we can directly use this to find connected components. So basically, we run a depth first search at some start node, and all the nodes that we can reach from this node are connected. And then we need to find the next unvisited node, and again repeat the depth first search from that node, and then all the nodes that you can reach from that is the next connected components and so on. So this can be very useful. We can also use this for flood fill. So basically it's the same thing. But usually we represent this 2D grid. I mean, it's a 2D grid that is considered to be a graph, and then we use depth first search or breadth. I mean, yeah, both works, of course, to kind of find all the nodes or pixels that are connected to this one that should have the same color, for example. We can also use this to do topological sorting of directed acyclic graphs. So in this case, there is a graph where all the edges have a direction and there are no cycles. So you cannot go back to a previously visited node. And here it's a topological sort. It's about finding the order in which you have to carry out something so that all the prerequisites are already taken care of. So for example, it might be a graph representing the different actions in a plan, and you might have prerequisites, so you need to do a number of things before you can do the next thing. And topological sort will give you a total order of the nodes so that all these dependencies are satisfied. And here there are a number of different algorithms. Tarjans is based on DFS. Cons is based on BFS, breadth first search. So it's basically different ways of going through and maintaining this information. We can also use this depth first search to do bipartite graph check. And this is a question whether you can separate the nodes into two sets, where edges in one set always goes to the second set, and so on. So there are no edges within the set, only between the two sets. And this we can do also with depth first search. So we'll talk more about bipartite graphs at a later lecture. We can also use depth first search to find different types of edges, tree edges, back edges, forward cross edges, and so on. And then there's something called an articulation point. And an articulation point is a point who is a node in a graph that if we remove this node, then the graph will be disconnected, so that you cannot go between the two different parts of this graph. And a graph that doesn't have an articulation point is called biconnected, which means that there are at least two ways of reaching every pair of nodes. And a bridge is then an edge in a graph whose removal disconnects G. So this is then the bridge is the edge, the articulation point is the node. We can also develop algorithms to find strongly connected components in directed graphs. So we saw that in an undirected graph, it was very straightforward. In a directed graph, it's slightly more elaborated. So we need to keep track. So basically, it's a Tarjan's algorithm for finding the strongly connected components. Can be used is based on depth first search, but you need to keep track of information when you're leaving one strongly connected component and start the next one. And one very interesting usage of this strongly connected component method is to solve the two-set problem. So in two-set problems, we have sets. It's a satisfiability problem. So the question is, can we assign truth values to a set of variables so that the formula becomes true. And two set means that we have clauses of exactly two. So it's basically pairs of variables that are related. And what we can do is to write this in a conjunction normal form, and then write this as implications. And then each implication between this pair of variables becomes an edge, and every variable becomes a node. And then we can find the strongly connected components in this directed graph. And if a variable and its negation are both in the same strongly connected component, then it's impossible to find an assignment. If that is not the case, if they are all in different strongly connected components, then we know that there is a solution to this particular two-set problem. So that's a pretty nice usage of this strongly connected component method. So that was a bit of an introduction, general things related to representing graphs and to traverse graphs. Now we will go through the main algorithms needed for the labs. So the first set of labs is about finding shortest paths. So what we're interested here is that given a weighted graph G and a starting node, often called a source node S, what are the shortest paths from S to every other node of G? So we want to find these shortest paths. And usually this problem is abbreviated SSSP for a single source shortest path. If we have an unweighted graph, which is the same to say that all the edges have equal weight, then the best way of doing this is to use breadth first search, because then you will keep track of the distance to every other node, and you know that you keep track of the distance from the start node, and for each kind of layer that you add, you increase this with 1. And we can just if we want to actually recreate the particular shortest path, then we can keep a vector where it's basically the parent of every node, and then so basically it becomes a linked list that we can follow backwards to find the starting node from whatever ending node or whatever node we're in. If we have a weighted graph, so it means that the different edges have different weights, then we need something a bit more elaborate. So here the best algorithm is called Dijkstra. So Dijkstra is actually quite similar to this best first search, in that we keep track of a priority queue with reachable nodes sorted on the total distance from a source. So basically, we visit the nodes based on the shortest distance to the start node or the source node. And then we try to find reaching the next node, and then we just update the currently minimum distance. So either we have found a new path to reach this next node, or we have found a shorter path before, so it means that we can then update these distances. And if this distance is decreased, add all neighboring nodes to the priority queue. So this again is a very simple and elegant method for computing all the shortest paths in a weighted graph. However, there is one important condition, and that is that there are no negative cycles. And a negative cycle is that basically there are negative edges in the graph, so that you can, if you go through a negative cycle, the sum of the edge weights in the cycle is negative. So some of them may be possible, so you might have 2, -3, -1, 1 or something like that. And then the sum in that cycle would be -1, and so on, which means that you can basically find shorter and shorter path by going in the cycle infinitely long, and then you will get infinitely low number. So Dijkstra, as presented on the previous slide, works even with negative weights, but not with this negative cycles. So if there are negative cycles, then we need to use Bellman-Ford, which is basically a dynamic programming-based approach, where we relax all the edges b minus 1 time. So basically, we do a dp over every edge and update the distance as the distance to go either directly to this node v, or visiting some intermediary node u. So that's the difference. So basically, every time we go through this, we will increase, in some sense, we will improve the quality of this distance estimations. So after we have gone through this process b times, then we know that if it still changes, then there is no cycle. But if it's still possible to make changes in the vth iteration, there must be a negative cycle. So then you know that. So this is again a very useful and very elegant method. So it's slightly less efficient than Dijkstra. So the kind of recommendation is, if it's possible, use Dijkstra. If you have negative weights, then use Bellman-Ford. So these were all about single source shortest path. We will now go through a method for computing the shortest path between every pair of nodes. So in some sense, of course, we could have done, say, Dijkstra, starting in every possible node, and then computing the shortest path to every other node, but this would be less efficient. So here we would use an extremely elegant and extremely short algorithm, namely the Floyd-Warshall algorithm for computing the all pairs shortest paths. So it basically is a 3 nested loops. And basically it loops over every start node, every end node, I and j, and then every intermediary node, k, and then updates this adjacency matrix for this by taking the smallest number, either going directly from I to j using the best path found so far, or you use this intermediary node k. So basically this is a 4-line, well, you can write it in short if you want, but 4-line algorithm for computing all pairs shortest path. So why is this useful? Well, it can be used actually to solve the single source shortest path if you have very small weighted graphs. But what's more interesting is, of course, if you want to do the transitive closure. So, for example, finding everything that you can reach from some set of nodes. We can also do minimax and maximin. Combining minimax here. So that can also be useful. We can find the cheapest cycle or the negative cycles. So this can also be used for finding negative cycles. We can use it to find the diameter of the graph. So the diameter is the longest distance between any pair of nodes in a graph. We can also use this for finding strongly connected components, but of course it's less efficient than Tarjan's algorithm, for example, because this will always be v cubed, because you need to go through this every triple once. So if we make a summary of these approaches to shortest path problems, so we can see that breadth first search we can use if it's an unweighted graph, then this is the best approach we can do. If the graph is weighted, then we cannot use breadth first search. Dijkstra, on the other hand, is the best we can do if we have a weighted graph. And Bellman-Ford is the best if we have negative cycles. So then we need to do Bellman-Ford. And finally, we have the Floyd-Warshall all pairs shortest path, which of course is the best if we have very small graphs or if we need to actually find all pairs of shortest paths. So these are kind of some of the bread and butter algorithms that are really core to algorithmic problem solving in general. So finally, I will also briefly talk about minimum spanning tree. So a minimum spanning tree is given a connected, undirected, and weighted graph G. Select a subset of edges such that the graph is connected and the total weight of the selected edges is minimal. So a typical example here is if you want to build a telecom network, so you want to draw cables connecting different nodes. Then you have all the nodes that you want to connect. You have the distances between every pair of nodes. And now you want to determine what is the shortest total length of cable that I need to connect every node in this graph. And that's the minimum spanning tree. And again, this is extremely useful method that's used in many other problems as well. Yeah, and this then corresponds to finding what's called the minimal spanning tree. So a spanning tree is a tree that covers the nodes such that the sum of those edges is has the total, the minimal total weight. Yeah. So here there are two main algorithms for doing this. My favorite is Kruskal's algorithm, which has time complexity E log V. So what we do here is that we sort the edges based on non-decreasing weight. So again, narrower again, but this is an example where we use edge lists. So we sort them from cheapest to most expensive edges. And then we just take the first edge in this list. And if this edge connects to previously connected components, then we keep it. If adding this edge creates a cycle, then we know that then it doesn't add any information because those two nodes are already connected. So there's no point in adding this edge. And this we can do with the union find data structure. So we're basically keeping track of this. So we start out with each node being a separate set. And then we check if we add this edge. So basically, if we do the union of these two nodes, if these two nodes already connected? If they are in the same set, it means that they are already connected, and we don't add this node. We don't add this edge. On the other hand, if these two nodes are in different sets, then we do the union, which means that we add this edge, we do the union of those two sets, and then we proceed. So this is a very nice example of a greedy algorithm. So we can go through these edges just from cheapest to most expensive once and do this step and greedily adding edges until we have our optimal minimal spanning tree. Very nice. There's also an alternative algorithm called Prim's algorithm. So here, when we visit a node, we add all the next nodes sorted by the weight of the edge in a priority queue. So here we go through the nodes one by one, but we add the edges based on weight. And again, we repeatedly take the minimum weight node, which hasn't been visited before. So basically, previously was taken in the Kruskal's algorithm, we take the edge, that is the cheapest. Here we take the node, which is the cheapest to visit next. So this is another nice algorithm. And then, of course, there are a large number of variations of these. So we can find a maximum spanning trees instead of finding the cheapest, we want to find the most expensive. We can find minimum subgraphs, spanning subgraphs. So rather than trees, we can find graphs. We can find minimum spanning forests, so finding multiple trees that together span this set of nodes. We can also find minimax and maximin paths between these pairs of nodes. So all of these are very useful and nice. So to summarize, in this lecture, I've been talking about graph representations, adjacency matrices, adjacency lists, and edge lists. I've talked about graph traversal, breadth first search, depth first search, best first, A-star search. I've talked about single source shortest path, Dijkstra, which is the kind of default case, unless you have negative cycles. In case, then you would use the Bellman-Ford. And then we have the all pairs shortest path, Floyd-Warshall. And finally, we have the minimal spanning tree, either using prims, basically visiting the nodes from cheapest to most expensive, or Kruskals, where we greedily select the edges instead. And in the labs, you will implement several of these algorithms. So I wish you luck with that and have a nice day. Thank you very much.